Hi, yeah, welcome again. Shall we start? Please log into your virtual machines and we'll start. So let other people join. Uh, I'll just recap what we have done so far for molecular dynamics and then we'll go to the further analysis part. So we are working with this particular protein 3-LAU, right? To download the protein, we need to go to file get PDB, right? So that is the first thing you need to do, download the protein. After download the protein, you need to go to the protein prep to prepare the system. You carefully build your system by defining all those parameters. The pH, that is one of the important property. That should be your assay or the experimental pH. If there's a missing side chains or missing loops, then you need to tick box that one. And finally, you can prepare your system. Right, so that part is protein prep or protein preparation. After you get the prepared protein, to run molecular dynamics, you need to build the system, and that is called system builder. Right? So you take the prepared protein, you build the system, define the water model. In literature, there are so many water models, but the default with the OPLS 4 force field, that is the SPC water model. You define your simulation box, either cubic or orthorhombic, anything is fine. And then you put the ions at salt concentration, and then you build your system and get your system set up. Right? Then you will get your simulation box with the protein, all the water molecules, ions, everything. And then you go for molecular dynamics simulation. And to do that one, you need to go to task, then molecular dynamics. You load your system, and typically for drug design or protein ligand complex, protein DNA complex, typically people run 100 or 200 nanosecond simulation, and you define your ensemble, NPT, NPT. Typically people run with the default NPT. The pressure and temperature will be conserved, and you define your temperature and the pressure. With that, you can just submit the calculation, and again, it will only run in a Linux system, and you need a GPU card to run the molecular dynamics simulation. After simulation, like typically it will submit for 100 nanosecond. Typically it will run for 8 to 10 hours simulation, and you will get the final trajectory. And then you need to do a lot of this analysis of the trajectory file. So one thing you can do is that first, obviously you need to first run the trajectory file, right? And see what is happening, the visual inspection you need to do. So I just load the trajectory, and I'll just go to preset, apply default custom, and you need to carefully see that during the simulation exactly what things are happening. Which are the hydrogen bonds that is maintaining during the simulation. You can also see some of the water molecules that is making hydrogen bonds with the ligand. You just play this trajectory and see the entire trajectory. Your ligand is stable at the binding pocket or not, and which are the interactions that is making sense, right? And if you do that one, then you can calculate very basic properties like distance, angle. By go to the measure option here, you define some distance, angle, or maybe the ring distance, and calculate all those different distances. Okay, so this part we have covered, and now we go to the more analysis part of this simulation, that is the quantitative analysis. more quantitative analysis, and there we'll see the RMSD, RMSF, and also the protein ligand interactions, which are the residues that are having that interaction during the simulation that we will get from this quantitative analysis. So all of you, please include your trajectory file. Please do that one. Include your trajectory file. There is a one tool called simulation interaction diagram. So you need to go to task and browse it to Desmond. Browse Desmond. Click that one. And on the right side, there will be one option called simulation interaction diagram. Okay. I'll again repeat. Task, browse, go to Desmond, and simulation interaction diagram. You need to open this panel. So or you can, if you know, I can also search. I'll just type it here. Simulation, this particular simulation interaction diagram you need to open. So I'll open that one. This is a panel for simulation interaction diagram. Okay. I'll wait for a few minutes and you can use the chat box and let me know that you can see the simulation interaction diagram panel. Please open the simulation interaction diagram panel. It is in the task, Desmond, and then simulation interaction diagram. Please open this panel. Yeah. So there is option, it is coming that load. Click that load option. And you need to go to that particular path again where we kept the trajectory file. So you need to go to desktop, data, docking MD workshop files, Desmond MD3LF folder. And again, you need to open the same file, that is the Desmond underscore MD job out.cms. Okay, I'll again repeat the path. It is in the desktop, data, docking MD workshop files, Desmond MD3LF, and you need to open the MD Desmond underscore MD job out.cms. Please open that file. This is a file, .cms file. This is the last snapshot or the coordinate it is saved from the simulation. So if you run for 100 nanosecond simulation, this file mdjobout.cms, it will have the coordinate for your last frame, coordinate of all the atoms. I am opening this file, and if you have problem, let me know. So it is in the desktop, data. I'll just put it in the chat box so that all of you can follow. Please open that file. Yeah, I put it in the chat box. Okay, so that is a path you need to follow and open that Desmond MD job out.cms. Okay, I think there's some problem happened. I'll again open. So I'm going to task simulation interaction diagram, and the path is load desktop data docking MD workshop files, Desmond MD3LU and Desmond MD job out.cms. Okay, so that is the file you need to open, and if you open this file, it will ask for the protein. So automatically it will select the protein from your trajectory file, and also it will automatically select the ligand, and it will run on the calculation from the your first frame or the 0th frame. And I just select all, right? Select all the properties, and I will explain all those properties, RMSD, RMSF, all those different properties. Click on run and change this local host to compute CPU and start run calculation. Okay, so I'll again repeat. I'll open that file, Desmond MD job out.cms file. And then just select all, run, and make change here host, local host to compute CPU and start from this calculation. Okay. Because it is calculating all those properties, it will take some time, maybe 5 to 10 minutes, and then you will get the result in this particular panel, simulation interaction diagram. Okay, so I already ran the calculation, and let your calculation is run, and meanwhile I'll explain the result. Okay, so I load that particular file. So if the job is completed, you will see some images here and also in the working directory. So I'm just seeing where is my working directory. When I'm clicking start, it is saying invalid CMS. So Moses, can you, so Moses, yeah, can you share your screen? I'll stop share and please share your screen. Yeah, can you just click OK for the time being? Yeah. Yeah, you need to click on Desmond and no, not me. Desmond underscore MD job order. Yeah, you need to click that one. That is from your simulation file. Right? Select all, run, change localhost to yeah, and start run. Yeah. So it will take 5 to 10 minutes to complete this calculation. And when this run will be completed, you will be seeing some file name in your working folder that will also be generated with the name Desmond, your job name, and the .eaf. Okay. So this file it will be generated in your working folder. Either you can open this folder, or automatically, if your job is completed, it will show in this simulation interaction diagram. So I just open that file, and you will see after your calculation is done. Okay, so I'll explain this result, all those different results, and then we can go to the other topics. So if your after your job is complete, this simulation interaction diagram, you will see this kind of all those different properties from your simulation and different tabs. This is protein ligand RMSD. This is secondary structure RMSF, ligand protein contacts. So all those properties it will be automatically calculated. So we'll explain this first one, that is the both protein ligand RMSD. So in this particular plot, we are seeing this left hand y-axis, that is a protein RMSD, and this right hand red color, that is my ligand RMSD, and this is over time. Okay, so I'll explain what do you mean by RMSD and how you can explain that particular RMSD. So I have this particular slide. Right, so the RMSD, it is the root mean square deviation. This is the main equation, which is the root over of 1 by n. N is the number of atoms in your system, and it will go over all the atoms. I is equal to 1 to n, and it will calculate delta I square. Okay, delta I square. So delta I is your difference of your distance between the from the first frame to the next subsequent all the frames. So suppose I have the one atom here at the frame number 1, and that atom it will have a different coordinate in frame number 2. It will calculate the distance between the two atoms from the frame number 1 to frame number 2, from frame number 1 to frame number 3, 1 to 4, 1 to 5, like that. Okay, so that is my delta. From initial frame, your first frame to the all the subsequent frame number 1 to frame number 2, frame number 1 to frame number 3, 1 to 4, 1 to 5, 1 to 6, like that. All the frames it will calculate, and that is nothing but my delta, the distance between the pair of atoms on the different time frames. Then we will take add all those things, all the atoms, divide by 1 by n number of atoms, and take the root over root. What essentially it does is that it is try to calculate or try to see how much your structure is deviating from your original starting point. Our original structure was from the crystal structure, and then we applied the temperature, pressure. Also, we had all the ions, and we are trying to see that how the system is behaving on the influence of temperature, pressure, ions, everything. So how much my initial structure is deviating from the how much our structure is deviating from the initial structure. It is trying to essentially capture that phenomenon. And you will see this kind of behavior or the plot here, like simulation time versus RMSD, which will be in the angstrom unit. Yeah, typically it is in angstrom unit. And you will see this kind of behavior that initially the frame number 1 to frame number 2, the deviation is very less. Frame number 1 to frame number 3, deviation is little bit more than the previous one. And gradually it will increase, and after some point of time, it will fluctuate on at some particular value here. And if you see this kind of behavior after the increasing in the initial frame and then fluctuating on some average value here, then you can conclude that you have this stable structure. Now your system is stable, and all the properties that we will be calculating, that will be meaningful. If you have non-equilibrium or your structure is not stable, the properties that we will be calculating, those have no meaning. So you need to have a stable structure to calculate all the properties. So typically the RMSD, that is quantify your stable structure during the simulation. Also, you can see this kind of behavior sometimes, and you can see there's a less fluctuation in the RMSD as compared to the first picture here. This is again stable structure, but since it has less fluctuation in RMSD, we can conclude that it has more rigidness or there's less fluctuation in the structure as compared to the first one here. But if you see this kind of behavior, that your RMSD plot, it is gradually increasing, which means that structure is not yet converged. Okay. And if you see this kind of behavior, probably you need to extend your simulation, maybe longer simulation. If it is not sort out your problem, maybe your initial structure preparation is something wrong happened. Okay, whatever parameters that you have defined, that is something wrong. Okay, so you need to go back, check all the settings option of protein preparation, ligand preparation, or whatever step that you have done, check carefully if there is some mistake that you have done. Okay. So that is how we're going to explain the RMSD plot. Okay. So there is one question that how much fluctuation is permissible. So there is no as such cutoff value. Okay, that what is the RMSD cutoff? But typically it should be below 3 angstrom. Okay. If you see below 3 angstrom, which means that your structure is deviating 3 angstrom from the crystal structure, that is acceptable. Okay. Otherwise, again, your structure is too much deviating from the original structure. Something different happened in your structure, some very large conformation change or something happened. Then again, you need to run the trajectory file or visualize the trajectory and see that what is that happened in the structure. Okay, so typically it's 2.5 to 3 angstrom, that is the acceptable value. Okay, so that is how we're going to explain this result or the RMSD value. And so we'll go back to the our result here. Now what we are seeing here is that this is for C alpha atoms. Okay, so I can uncheck that one and I can also check the backbone atoms or side chains, right? So anything we can do, but typically people what they do to check the stability, either you go with the C alpha atoms or the backbone atoms. That will give the stability of your backbone of your protein. So people do only for either C alpha or backbone. Okay. So in this plot, what we are seeing is that initially it is gradually increasing. It is starting from 0, and after some point of time, here it is fluctuating on average value of 2 point, maybe 2 angstrom something here, right? It is fluctuating here, which means that after 1 nanosecond or 1.5 nanosecond, we reach this stable structure. We have the equilibrium structure now, and whatever properties that we will be calculating, that will have some meaningful result, right? Same thing for the ligand RMSD. It is typically it is whatever value that we are getting. But if you see this ligand RMSD, if it is gradually increasing, which means that your molecule is not sitting at the binding pocket. If you start with the docking dock pose or in the crystal bound pose, if you see this ligand RMSD, it is gradually increasing, which means that your system is not stable at the binding pocket. Your ligand is not stable. It is aligned on the protein. So the ligand RMSD, it is aligned on protein, which means that it will aligned on the protein structure, and that will give you the information that your ligand is stable at the binding pocket or not. Then protein secondary structure. So the protein will have different secondary structure like strand, helix, loop, right? And this talks about that during the simulation, your secondary structure is preserved or not. So the first plot, that is my residue index. This protein has 251 residue. So these are all residue index going from 1 to 251. And the color code here, the cyan color, it is the strand. The orange color, that is helix region. And if there's no color, blank, which means that that is in the loop region. So this particular region here, maybe 50 to 60, that is in the helix. Next from here to here, that is in the loop, that is in the strand. And if there is no color, that is in the loop region, right? So you can see also here, almost it preserved the secondary structure during the simulation. So 100% means that percentage of secondary structure. So 100% means that your entire simulation. So this simulation is run for only for 5 nanoseconds. So during the 5 nanosecond simulation, your all these residues preserve their secondary structure, except here, here, and the last terminal here. So if I see the terminal one here, maybe 245 to maybe 248, some 3-4 residues, some 50% it is having the helix form, right? And rest it is in the loop form, which means that there is some changes happen, the secondary structure changes happen going from loop to helix or helix to loop. Okay, and this is very important if it is happening in the binding pocket residue. Okay, typically by your ligand should be stable. If you want to design some molecule, your drug molecule, that should be better binder. And if your ligand and if your binding pocket residues don't preserve the secondary structure, then your probably your ligand will be unstable in the binding pocket. This is overall secondary structure. It will combine everything and it will give you the overall percentage of the secondary structure during the simulation. The next plot or the last plot, this is with respect to time. And now my y-axis or my residue index. So it will go from 1 to 251. And it is telling me that at what point of time it is having the what kind of secondary structure. Right. So if I place my mouse, it will also tell that this is my arginine 179. It is in the helix form. What is the time frame? 1.210 frame, 1.0 second, and it is almost 99% in the helix form. Right. So those kind of information you will get. And if I place my mouse at the end here, which is basically 240 residue number, yeah, some changes, numbering change happen, but it is the last something 245 residues, and only 46% it is having the helix form. Right. If I place my mouse here, it will show. So the last spot here, this is having the 46% in the helix, rest is in the loop. So those kind of information you can get, and you need to specify or clearly identify where is a binding pocket and if it is going to have make changes or not. This kind of analysis, it is very useful if you want to see this kind of your protein folding unfolding problem. There you will see this kind of secondary structure content going from your particular 3D conformal structure to the extended form, the unfolded structure. The next step is protein ligand. This is a protein RMSF. So RMSF means that root mean square fluctuation. It is nothing but it will try to calculate your thermal fluctuation during the simulation. We have temperature, and if you have the temperature, your molecule or the atoms will fluctuate, and this tells that which residue are mostly fluctuating. So it's again the angstrom unit, and the higher the peak, here, those particular regions are mostly fluctuating. Here, these regions are mostly fluctuating, which is the residue number maybe 10, 20, something like that. And there is also this green color line sticks. So these are my ligand contact. So it is already activated. Or if I just click that one, this tells that these are the residues that are in contact with my ligand. So all these residues that are in contact with my ligands. And you can also see that the binding pocket residues here, they are not so fluctuating, right? Which again means that probably this particular molecule will be stable, and it's telling that this is stable during this 5 nanosecond simulation. Because the residues are not fluctuating too much, they are stable in the binding pocket. So my ligand will be probably stable in the binding pocket. And I can also plot the secondary structure. So again, the color code is same, like the orange color is that your helix, if there's no color, that is loop, and the cyan color, that is strand. So I can also plot it here. And one thing you can also identify or note that uh, the loop region, this here, they are mostly having the high fluctuating region, right? And that is true because the loops are mostly fluctuating because of the temperature. They don't have particular structure, and because of that one, there is no hydrogen bonds or pi-pi bond stacking, pi-pi bond, and because of that one, they are mostly the fluctuating region in your protein. This region, all this loop region typically will have the higher fluctuation as compared to the proper strand uh, helix region, right? And the after this protein RMSF, also we can get the ligand RMSF. It's the same thing, like If you have this particular ligand, all the atoms that will fluctuate upon temperature, and higher the number or higher the peak, it will have the mostly fluctuating region. So I can see that if I place my mouse here, it is telling that this particular atom, the atom number 20, it is mostly fluctuating, and the reason may be that this terminal group may be in the solvent exposed region. This particular region probably inside in the binding pocket or in the protein environment, but this terminal here 20, where it is mostly fluctuating. So probably it is in the exposed towards the solvent. And if I see this all the aromatic group, right? So all these are less fluctuating because these are aromatic ring. So they will have less fluctuation during the simulation. Also, this will, if you want to design a drug molecule from here, you can see that which are part of your ligand is mostly fluctuating. Probably this carbon number 20 or 22. Here also some it is mostly fluctuating. So probably you need to identify those fluctuating region and can you incorporate some interaction there so that this fluctuation will be less. So that is how you're going to you design your new compound or when you're going to design the drug molecule. The next step is the protein ligand contacts. So the first plot here, this is telling that these are the only residue number, leucine 139, valine 147, all the residues having what kind of interaction it is making with the ligand. So you can see the color code here. The green color is hydrogen bonds. The blue color means that this is water bridge. This yellow color or the orange color is halogen bonds. If there is a red color, that is ionic bond. So alanine 213, it is purely having the hydrogen bonds, right? So it is telling that alanine 213, it is only having the hydrogen bonds with the ligand. And if I see this, maybe the lysine 162, some part it is hydrogen bond making hydrogen bond sometimes it is hydrophobic. Also there is a water bridge, means that this water molecule is making hydrogen bonds with both the ligand and also the residue at some point of time. That is called water bridge interaction. And if I just deactivate all those things, I just only activate the maybe the hydrogen bonds. I can do that one. Yeah. So if I just only activate the hydrogen bond, then it will have more further information. It will tell you about the backbone donor, different color code backbone acceptor, side chain donor, side chain acceptor, right? So I can see now alanine LR213, it is mostly having the backbone donor. Sometimes it is backbone donor and sometimes it is having the backbone acceptor. Whereas this ASN261, it is having the side chain acceptor. Lysine 162, it is having the side chain donor. So all those critical information you can get from this protein ligand interaction plot. Same thing I can do for hydrophobic. So I just only activate the hydrophobic one. And if we just activate the hydrophobic, now it will have divided by some pi cation or pi stacking or maybe some kind of normal van der Waals kind of interaction, hydrophobic. So further it will have that kind of information, right? So all those information you will get from this plot. And this tells that this particular graph, it is telling that during this simulation, your ligand is making how many contacts with your protein. So in total, I can see that it is having 6 to maybe 9 contacts during the simulation. Okay, how many ligands, how many contacts the ligand is making with the protein. And now this is divided by this plot here. This is time again, and now all the residue index. Total is 6 to 9. So if there is above 4, which is this color code, which having the above 4 interactions with the ligand. So this alanine 212, sorry, alanine 213, this is having the number of contacts more than 4, something like that you will get. Okay, so what I can tell here is that maybe the LR213 that is having the most important residues, it is having the hydrogen bonds, something like that you can guess from this protein ligand interaction and the context. So context means that all the atoms, right? So if I go to this ligand protein context, so all the atoms have the van der Waals radii, and also the from the side chain of the protein residues, all the atoms have the van der Waals radii. And if they are coming closer, there is a cutoff value or the distance cutoff. If it is falling in that range, it will have the one contact. Okay, so that is purely coming from your van der Waals radii. If it is falling within that cutoff region, it will have a one count. Okay, so that is the protein ligand context. Then we'll go to the ligand protein context. Now it is with respect to the ligand. Earlier it was with respect to the protein, all the residues. Now we have the ligand centric view. It is the same thing like your 2D interaction diagram, but now it is having the information also having the trajectory. So what I can see here is that all the residues that are making the interactions, glutamate 211, like it is telling that 100% it is having the that particular interaction, and the interaction type is hydrogen bonds. Okay, so this means that this hydrogen bonds, and LR213 also, this is also having important, and this is also making hydrogen bonds with this either this part of your ligand or this part of your ligand. So sometimes this is hydrogen bond donor, and this part of the ligand it is hydrogen bond acceptor. Okay. Also you can see some water molecules that is kind of bridging between the your ligand and also the residue. So 100% means that 100% during the entire time, this particular interaction is preserved. 59 means that 59% of your total simulation time, that particular interaction is preserved. Okay. Again, this will give you the idea that which residues are important for the ligand binding process. And you can see this particular here, all those are terminal region that is solvent exposed. And because of that one, you will see that these have the higher fluctuation. In the RMSF plot, right? This terminal have the higher fluctuation because it is in the solvent exposed region. Okay. So next is that ligand torsions. So again, this is very important. This ligand torsion, it is very important. And you can see this kind of plot here. It will automatically identify the all the dihedral angles or the torsional angle from the ligand. So in this particular ligand, we have the 6, and it is designated by this different color code. So this particular light green color, this is here. This one, it is here. Deep green color, that is particularly this dihedral angle. And this is the probability. Okay, this particular code, this is the probability. And it can go from -180 to plus 180, the dihedral angle. Okay, so this tells that during this simulation, which are the particular regions that is explored by this dihedral angle. So if I see this particular here, which is sandwiched between this two aromatic ring, because it has less flexibility or freedom to rotate, and that is why it is only exploring this particular region here. Okay, but if I see the terminal group here, because it has the single bond and it is exposed toward the solvent, it has a lot of freedom to rotate this particular dihedral angle. So it can explore this region, this particular region, here. So all those region it can explore. Same thing you can see for other dihedral angle. Okay, so again, this tells you about that part of your protein is mostly flexible or it can rotate during this simulation. The last one, that is the all the ligand properties, ligand RMSG, radius of gyration, that is give you the your ligand is extended or in the coil form. If there is intramolecular hydrogen bond here, there is no intramolecular hydrogen bond for this particular ligand. Some molecular surface area, solvent accessible surface area, and also the polar surface area. Okay, so those are typical kind of your uh, drug-like properties. So it will also calculate all those properties from the simulation. Okay, so that is how we're going to explain all those different plot. RMSG will talk about the stability of your system during the simulation. Secondary structure also tell you the stability of your secondary structure content. If there is some changes happen, you can identify or the locate all those which residues or which part of your residues it is having that change happening. RMSA will talk about the thermal fluctuation of your residues. Mostly fluctuating region will be in the loop region. Ligand RMSA, we will talk about your flexibility of your thermal flexibility of your ligand, which part of your ligand is mostly fluctuating during the simulation. Protein ligand contacts, this is important, which are the residues are involved that are making interaction and what type of interactions you will get it from here, number of contacts, all those things. Ligand protein contacts, which are the residues having the percentage wise during the simulation, this particular interaction is preserved or not. And ligand torsions talks about the flexibility or which particular torsional angle can rotate more easily. And finally, you will get the ligand properties. Okay. So this is the all these different plots you will get. And you just need to click that one. You open this SIMD panel, simulation interaction diagram panel, load your CMS file and just calculate all the properties. You will get all those different plots here. Okay. So any questions from here? All of you, your job is completed. Can you see this picture? If you have any question, please let me know. Job is completed. So can you see this? All those different plots are here. Okay, good. So yeah, so as this call is recording, okay, so we'll share the recording. Probably later you can go and check all those different plots. How we're going to explain all those different plots. Okay, and also you can so if I click, all of you can do that one. There's option here, generate report. How to generate the CF file. Yeah, so if you run this SID file simulation, like if you run this simulation, it will automatically generate this EF file and that will be saved in your working directory. Okay, so if you run this calculation, it will save in your working directory. Okay, so yeah, any other question? So if you want to generate the report, you can click here, generate report, and it will generate a PDF report. Also, you can save all those different figures. So I can generate a report. I can generate all the plots, and I can also save all the different raw data. So if you're not happy with this plot here or the color code or all this plot, if you're using some separate other tools for plotting, you can also do that from this raw data. So I'll do that one. You can also do and see that. I'll click OK. So it will be saved in your working folder. So I just save that PDF report and the data, all the images. So yeah, you need to go to your working folder. So this is a Linux system. So you need to click this particular icon here to go to the corresponding folder. All right. So if you create a folder, day2_dynamics, go to that folder. And inside that folder, there will be another folder called data1. So in this case, I didn't save this working directory. So that is why it is created. Yeah, it is done. So it is created in my local user directory here. But if you save this in your day-to Dynamics or any folder, working folder, if you go to that folder and inside that folder, a folder will be created data one, and inside that folder, you will get a PDF report, raw data file, and also all the images. Okay, so I'll just open that PDF file just to tell you that what is that in that PDF report. So this kind of PDF report that you will be getting, and yeah, there is some basic information like simulation details, what kind of ensemble that you have used, the temperature, the pressure, total simulation time, all some information, basic information first to be there. Then some information for the protein, right, on the residues, number of atoms, number of heavy atoms, total charge you will get, and the sequence of the protein. And if I go down, you will also see the ligand information. So all the ligand information you will get, total concentration, then the protein ligand RMSD, like all the plots, some basic definition of this RMSD, and also someone asked, right, the RMSD cutoff value. So also you see that changes of order 1 to 3 angstrom are perfectly acceptable. But if you see more than 3 angstrom, means that there is something consumption change or your structure is not stable. Okay. So all those some basic information it will also tell you in the PDF report. RMSD, then it will come the your RMSA. Right. So RMSA and also some definition of this RMSA, right? Ligand contact. So all those information you will get from the PDF report. Right. So all these properties you will get. Yeah, so someone asked this question. It is saying 30% contact residues are those. How can you relate it to stability? It would be stable or not, or minimum contact residues which are needed for stability. I see if I'm correct, you are talking about this particular plot, 30%, or which one you're talking about? Yeah, this particular plot, right? Yeah, so I'll go to the interaction diagram, ligand protein contact, right? So it is telling that, so you can see there is a cutoff 30%, right? Which means that suppose my simulation, it is 5 nanosecond in this case, and the entire 5 nanosecond is now 100%, right? And glutamate 211, 100% it is preserved means that your all the frames, it will have this hydrogen bond. Okay, so this cutoff, it is telling that which are the interactions less than 30%, it will not show in this particular image here. Okay, so typically, yeah, you need to have more number of contacts, means that frequency of this contact should be higher. But if I just make it 50%, so I can increase that value. So now probably I'll increase to maybe 81% or 80%, right? So you'll only see that which are the residues having the interaction percent more than 81. Only it will show it here. Okay. Typically, the 30% is default because 30% again. Right. So this 30%, it is try to capture the your Bridgewater interactions because water molecules are mostly fluctuating. this water molecule, it will come and go. So the percentage, it will be very less. Just to capture this bridge water interactions, the default value is 30%. Okay. So it's also tell that this water is particularly important. Also, you can see this particular water, 44% time it is having these interactions. Okay. So all those small interactions are important for the stability of this ligand in the binding pocket. Yeah. Any other questions? Yeah, if you have any other questions, let me know. This is very important. If you are, I guess probably all of you are new to this simulation, and you need to, again, if you are using Schrodinger tool, it is not difficult to set up the calculation, right? You can easily set up the simulation and run the calculation. But how to interpret the result, again, that is very important. Right, so I'll give a break here, maybe 3-4 minutes. Yeah, 5 minutes, exactly three. If you have any question, let me know. And then other things today we'll cover. And yeah, one more thing that I want to tell. Probably some of people also may heard about this MMGBSA on the trajectory or principal component analysis, all those some kind of advanced analysis. Okay, from simulation trajectory. Those who are interested to learn all those advanced calculation like principal component analysis, free energy landscape, MMGBSA, please reach out to us and we'll tell you how to run all those calculation on the trajectory file. Okay. So with that, I think I will end here for the simulation and we'll have a break for 4 minutes. We exactly meet at 3 and then we'll cover the QSR or the some machine learning methods. Okay. So I'll stop here. If you have any question, let me know from the simulation or any other things. And then we'll start the QSR. Okay, so shall we start? QCR or some machine learning approaches. So our next topic it will be on QCR method, and I have some few slides, 3-4 slides, just to introduce the concept of QCR method, and then we'll go to the directly to the hands-on. So shall I start? Yes, no. Yeah. So till now, what we have covered is that uh, molecular docking. Yesterday we covered molecular docking. Today we have seen the molecular dynamics simulation, and those are called receptor-based approaches, which means that I know the structure of my protein or the target, and if I know the structure of my protein or the target, then I can dock my molecule. I know the binding pocket. I can place my molecule in the binding pocket. I go and do molecular docking and then go for molecular dynamic simulation. Those are called receptor-based approaches because we know the structure or 3D structure of the receptor or the protein. But in many cases, if you're working some projects or some target, and you see that I don't have the structure of my protein, whichever target that I am working, I don't have the structure of the particular protein. In that particular case, if you have some compounds that you know some activity, some experimental data in here for some compounds or the ligands, then you can take that all the active or maybe those are moderately active compounds, then you can build some ligand-based approach methods. And those are like 2D fingerprint, pharmacophore, QSR, 2D QSR, or you can build 3D pharmacophore or 3D based QSR. Okay, so there are two different approaches in the computational drug design, receptor based and the ligand based. If you know the receptor structure or the protein structure, you go for the all the receptor based approaches, molecular docking, molecular dynamics, and it will give more information because you know that which are the residues are interacting, what kind of interaction it is making. So all those details information you can get from the receptor based approaches. But if you don't have the structure, then you can build the QSR model or pharmacophore model taking only the ligands into account. In this case, ligand-based approaches, you should already know some of the active compounds or some biological data of these compounds. Okay, so now we'll talk about the QSR method, right? So the method or the full form is that quantitative structure activity relationship, right? That is a QSR method, and it is a very like old method, more than 50 years old. What it does is that it try to connect between your structure of your ligand and the pharmacological response or the activity. If you have the structure of the ligand, it try to connect the relationship between the structure and the biological activity. Okay, how it is going to connect, that we're going to see. And this response, that is nothing but any kind of activity like PIC50 or EC50, KIKD value, all are like numerical or it can be categorical, right? It can be either active, inactive, toxic, non-toxic. So all those categorical response also you can have. And now it connects, it basically generate a mathematical model between your structure and the activity. Okay. So now people it called as the machine learning methods. But typically it's called the old it is method is called the QSR, quantitative structure activity relationship. So if I see here overall picture, I have some ligands, right? And for those ligand, I know the Y or the biological response. It could be anything. It could be Ki, Kd, right? Numerical, or it can be categorical, active, non-active, moderately active. It could be anything. But we know that what is the response that of all those compounds. For this compound, maybe the IC50 value is this one, 10.3. For this compound, it is this one. So all those compounds, I know the activity data. And we try to generate this mathematical model by this function here. So this function we need to identify that can relate between the your structure. In this case, structure means that molecular descriptors, right? So all those molecules are different descriptors that we're going to see. We generate all those descriptors of all those compounds and try to build this function or the mathematical model that could connect this to the biological activity. And we can then generate this model. And if we have this model for the unknown compound, which all we don't know the biological activity, we can predict for that particular ligand what could be the possible activity. Right? So that is the machine learning or the QSR method. You build the model with the known compounds, and if you have the unknown compounds, and on the model that you have built, we predict for the unknown molecule, and it will give you the prediction that okay, for the unknown compound, what could be the possible biological activity. Okay, so that is the in short this QSR method. And talking about this descriptors, right? So like those who are from chemistry, they can say, if I see this picture, they can clearly tell that this is the phenol molecule, right? But problem is that you need to make it understand this to the computer that okay, this is the phenol molecule, right? And computer only understand the number. It doesn't understand the image. But right now there is some image recognition method. But again, that convert to all the numbers, then it recognizes the images. Basically, it only input is the number. If you want to say something to the computer, you need to give the input as a number. So if I try to tell this computer, okay, this is phenol molecule, what I can do, I can count the number of carbon atoms, right? So there are 6 carbon atoms, 1 oxygen atom. All the counting, that could be one number, right? That I can give that input to the computer. I know the molecular weight of the phenol. I can give that as an input, right? If I apply the XYZ coordinate, that could be another input, right? Also, I can define the bond connectivity. There's how many carbon-carbon bonds, how many carbon-oxygen bond, oxygen hydrogen bonds. All those bond connectivity I can also give. Okay, so all this number, those are nothing but my all this x1, x2, x3, all the descriptors. Okay, this is nothing but to represent your molecule. It could be molecular weight, polar surface area, number of bond connectivity. So anything that could be your descriptor. Okay, so in literature, there are many descriptors are there. Some are like 1D, 2D, or 3D. So 1D is nothing but the simple number. So molecular weight, refractivity index, pK of the molecule, log P. So all those are one-dimensional descriptors that I can give there as an input. There could be 2D descriptors, the bond connectivity. Okay, that could be one. There could be 3D descriptors like van der Waals surface, solvent extrusion surface area, all listed field. Because those all these descriptors we can generate, all those x1, x2, x3, dot dot dot. Then we can build this function or the mathematical relation between this all the descriptors and connect to the our biological activity and we build this model. Okay, so that is the in short this QSR method. And one thing you always need to follow is that if you're working with some data set and if you have the IC50 or the PIKD value, always convert to the negative log unit, PIC50 or PKI value. Okay, so that is because to standardize your data set. Okay, so that is if you are interested, we can talk about that more in details. But also you can do some literature search. Always convert this IC50 to the log unit. Okay, or it's called the free energy unit. If you take the negative log, it will convert to the free energy. Okay, so some of the basic things that you always need to remember, and I'll talk about more in details during hands-on. Also, we have the 3D QSA. Today we'll not be covering that one, but if someone is interested on this COMFA, COMSIA, all those methods, how we can generate all those illustrative field for the compound and then build a model, we can take if you are interested on the next hands-on. So I now go to the hands-on. Please open the master again and we'll go to the hands-on. So there's one question, can you see electron cloud around ring? Uh, Rakesh, I'm not able to get your question. For electron cloud, right, you need to run the QM calculation. Okay. Normally in this all this classical mechanics, right? All those atoms or the charges are atom centric. They have partial charges on the atom. So you are not able to see the cloud. If you run the QM calculation, then you will see all the electronic cloud. Okay, so there's a, since you asked, there is a Jaguar panel, right? If I go to the Jaguar, okay, I can go from browse and Jaguar. Jaguar is for your quantum mechanical calculation, QM calculation. Okay, so please close the project. So I'll go to file and close project. Right, I'll create a new, I'll just go and create a new working directory for me. So go file, change directory, day, yeah, create a new folder anywhere, either in the user or desktop. I'll create here, new folder, keys there. All right. So I just go to file and change working directory. I just create a new folder and I'll give name file, save project as QSR. So this all two things you always need to do when you are opening a new project or working on a new project. Define your working folder and define your project name. That is always important. There is one question. Can you combine both the drug design approaches, SBDD and LB, to identify the stable compounds? Yeah, ideally, if you are working on a particular project, you need to combine all those different approaches. Like if you have you need to SBDD, if you have some set of ligands for which you already know the biological response or the activity, first build this QSAR model, right? Generate some compounds, ligand designer. So that will be our next topic, how you can design your compound. On the build model, you can predict activity. Then you can go for molecular docking, molecular dynamics. Ideally, it should be combine of everything, all the approaches, right? We never know that which method will going to work. Yeah. So please, all of you, please do these two things. Save, change working directory and save this project. Okay. So all of you have done this? Yes, no? Yeah. So I just, if you open the master file, I just told two things: file, change working directory, create a new folder. I just created in the desktop with the name QSA. That will be my current working directory. And then save this project as a new project. File, save project as. Okay, so that is for QSA project. So I gave the name QSA. So these two things always you need to do. Save the project in a particular folder, and that folder you need to create. So what we will do is that we'll import some ligand files that we have already kept. And for all those ligands, we already know the IC50 value. Okay. And on those compounds, we'll build this QSR model. So if you have done this one, I'll import some files, ligand files. So I'll go to the file, import structure, right? Go to file, import structure, home directory, desktop, data, which folder? It is in the phase 3D QSF, Endo. Yeah, you need to, if you're not able to see any file name here, change the file type to the all importable files. Then you will see the endo1 com.imagz. Okay, I'll again repeat. You need to go to file, import structure, change the file type to star star, means any importable file from the file type. Any importable file, go to home directory, desktop, data, phase 3D QSF. You need to go to the folder endo, and you'll be seeing one file endo_1 com.imagz. Okay, open that particular file. Right. So please open this particular file. I'll give the path here. File import structure. It is in this path. User. Go to home directory. User. Desktop. Data. Phase_3D QSF and endo. Open this endo1 underscore com.imagz. If you open this file, let me know. Yes, no. If you're not able to see the file, also tell me. So if you open this file, you can see in the project this workspace here, or there are 36 compounds, right? Please open this file. Yeah. So if you open this file, so these are the compounds, right? And if I want to see all the compounds at once, I can go to the window and click the 2D viewer. I'll again repeat. Click, it will be automatically selected all the 36 compounds. Selection means that title column, it will be highlighted by the yellow color. All the 36 are selected. I'll go to the window and 2D viewer. Right, so I can see all those 36 compounds in the 2D viewer panel. And one thing we can do here, there's also option called reference. So I click one and take the first one, endo1, as a reference. It will be highlighted by this blue color, and align all. Can you guys do that one? In the 2D viewer panel, there is an option called reference. I'll just make my first molecule, which is the title endo1. Right? I make the endo1 my reference compound, and on the reference compound, I am aligning the all the other compounds. So I'll just click align all. It will align all the compounds. Right? So one thing you will note that in this particular all these ligands, the core is same. Right? Here, this particular two fused benzene ring, it is same. Only changes are happening here and some part of here. Right? Can you go there and check? Right? So all those compounds will have the same fused benzene ring. And some cases, at the end, right, you will see there is only single benzene ring. Okay, this particular, oh, this is a, it is same here, here. Some cases it will have the fused benzene ring, and some cases it will have the single benzene ring here, and also little bit change here, this particular here. Okay, so To activate to see the 2D viewer, you need to go to the window and 2D viewer. Then make this first compound as a reference and align all. Okay, so this set of compounds, this is typically called congeneric series, which means that since they have similar kind of features or the chemistry, we expect that if this molecule go and bind to the binding pocket of the protein, they will have the similar kind of binding force or binding mode. Right? I'll again repeat. This kind of set, it is called congeneric series, which means that they have the same kind of chemistry or the core. There is a little bit change here and here. And we expect that if these molecules binds to the binding pocket of the protein, they should have similar kind of binding poses. Okay, there should not be flip or there should not be flip to other region, right? Now, this is one of the criteria of your QSR model. If you need to make this set or the ligand set for the congeneric series. Otherwise, if the binding mode is different, then probably the activity or the it will have a different kind of interactions and activity will be different. And their machine learning model for the QSR model, it will going to fail to predict for those compounds. If you take completely different compounds, not in this same series. Okay, so that is one of the criteria that you need to work with the similar kind of compounds or the congeneric series or in the same series. Okay. So that is one of the option, and you can see here in this case we take only 36 compounds. Okay, so there is one line in the machine learning. More the data, it will be more useful, or more accurate your model that you are going to build. Typically, if you have a good data set, even with the 36 compounds, you can build a good model. But ideal case, you should have at least 80 to 100 data points. Okay, to build the machine learning model. If you have a less than 30, 40, you can still build, but need to see that your model is meaningful or not. The model that you are building, it will build some kind of model, but you need to understand that that model is making. Okay. Now I can go to the, so here, can you guys see the setting here? There is a one setting fill kind of thing here. Click that one, show property, choose, and select the activity. And click OK. So I'll again repeat, this is same from I can get from the project table. There is a particular setting option here. We can import some of the properties from the project table by this option here. Click here, show property, choose the activity. Okay, I already selected. So select the activity one, properties. So you'll see all the properties or the activity of this compound. This is the PIC50 value of all those compounds. First compound have 5.5 like that. Okay. I'll again repeat, to see the activity in this workspace, click here, show property, choose the activity, and you will see all the properties in this particular panel here. Right? Are you guys able to see the properties? This is nothing but the your PIC50, IC50 value converted to the minus log unit. Okay, so same thing I can see from the project table. Okay, so if I go to the project table here, yesterday we have seen this project table for the docking calculation. I'll deactivate everything. I'll just select the, I think it is added by user here and activity, right? Same thing quoted here, right? Can you guys see the activity? Yes, no? Yeah. So again, this is some kind of activity. It could be anything. In this case, I took the IC50 value. This is taken from one of the publication paper. Okay, all these compounds. and their corresponding biological activity. It could be categorical. If you want to make a categorical model, you can take the toxic, non-toxic, solubility. Okay. Any property that you want to build a model, you can take it here and then build a model. Okay, so all of you are here. Then to build the model, you need to go to the task and you need to browse it to the Discover Informatics and QSA. I'll again repeat. Go to Browse, Discover Informatics and QSA. Click that one, and you can see all those different QSA methods are here. Like so, auto QSA. So today we'll be doing the normal auto QSA 2D. Deep auto QSA, it will also have some neural network based model. We're not going to do that one. If you have more than 1,000 data points, you can go to the deep auto QSA model. It will use the GPU to train your model. Normal auto QSA, it will have the CPU. If you have a less data, you go to the auto QSA. If you have a more number of data, go to deep auto QSA. It will have the GPU and it will train the model on GPU. Atom based and 3D field based, those are my 3D QSR model. Okay. So we'll open the today we'll see the normal auto QSR or the 2D QSR. So click the auto QSR panel. So I'll again repeat. Go to task. You need to go browse, discovery and informatics, and auto QSR. Right. So we are here. All of you open this panel. QSR panel. Right. Yes. So here you can see that first it is asking that you need to select the task. The first is that we're going to build a model. So keep that one, build model. And the build model is asking for use structure from. Okay. So for 2D QSR, if you are not prepared the, if you don't do the leak prep, still it will going to work. I'll again repeat, for normal auto QSR, if you are not using the leak prep, it will still going to work. But if you are going to 3D QSR, you need to prepare your DKN using leak prep. Okay. So if you are going to 3D QSR, because it will have the 3D information of your ligand, you need to do the leak prep. Okay, but it is not mandatory for auto QSR. You can prepare or not prepare, it doesn't matter. But in this case, to have a safer side, all these ligands have the leak prep. We prepare the ligand with the leak prep. Okay, so the option is a build model. So use structure from. So I just select the use projectable selected. All the 36 are selected, highlighted by this title is highlighted by the blue color. So all the 36 are selected. Select property to be fit. So I'll select, I'll go to the activity. So this is my activity. That property will going to fit, right? And to build any machine learning models, you need to define your training set and test set. What it will do, in the training set, it will keep some compounds in the training set. And on the training set, it will build the model. And after building the model, it will have the test set. So it will validate. So it will, for the test set, then it will going to get the activity prediction. So I'll again repeat. First, it will have the training set. It will build the model. After building the model, it will take the test compound. And for the test compound, it will test the model it will try to predict the activity for the test model. Okay. That is why you need to always generate this training set and test set. So default is 75% in training set. That is a normal people use 75% or 80%. So if I do that one, out of 36, 27 will be my training set and 9 will be my test set. Okay. So keep that one as a default. And in the property type, since these are numerical, there is no categorical. we'll keep this as a numerical one. Okay. And if I go to the advanced option here, so it will, this advanced option, it is all the descriptors are kept. Okay. So it will try to build all the models using linear regression, partial linear regression, all those different methods. It will try to build 50 different models. And what are the different descriptors that will generate? Radial, linear, dendritic, Morphin 2D, topological descriptor, physiochemical descriptors. So typically it will bet 800 or 1000 different descriptors. Okay. Physiochemical properties, all those property, topological or bond connectivity. Okay. So all those descriptors it will going to generate. You can also import from other files. Like from others you have generated, you can also import the descriptors from other files. Okay. So I'll just normally it's the default setting we don't get here. I click OK, right? And you can see here an advanced option. It will build 50 models and it will only keep the top 10 models. Out of 50 models, on the output file, it will only keep the 10 models. Okay, it will not save all the 50 models. It will only keep the top 10 performing models here. Okay, so with that one, this is very simple setup. You go to job setting, change this local host to compute CPU, make the processor 4 and run. Okay, so that is a setup for running for AutoQSR, and it will take 3-4 minutes to run this calculation, and then we'll see the result. Please submit this calculation. If you have any problem, let me know. I didn't change anything here. I just keep all those things default. I have selected this compound, 36 compounds, property to be fit activity. That is the property that we're going to fit. Training set test set 75% default and run the calculation. Okay, so let it run and I can see from the job here, it's waiting for it will going to start and it will take 3 to 4 minutes to run the calculation. Yeah, if you have any questions, just let me know. Are you guys running? Yes, no? Okay. Please run the calculation. Okay, mine is still waiting. Yeah, just started. Can we use for drug repurposing? Which method this use here? Yes. Yeah, you can use. So that is I'm going to explain, right? How if you go to the result, then I will explain that how we can use for drug repurposing. Yeah, mine's still running. Yeah, let it run, then I'll explain the results. Yeah, so there is one question. If we download uh, if we downloaded the steric structure of an inhibitor molecules, do we still have to make different conformers of that molecule before docking, or the time of docking software? No. First thing is that if you are downloading the structure, you go to the leak trap, prepare the structure, and you don't need to generate the different conformation, right? On the fly during the docking, it will automatically generate all the conformation for the ligand. Okay, that is a one protocol, search algorithm. The first stage, it will rotate all the dihedral angles of the ligand. It will try to generate all the possible different conformation of the ligand. It will take one by one and put it in the binding pocket. Okay, so you don't need to generate the different conformation. Do this work for peptide inhibitors? I mean, this QSA, Sati? So, yeah, so if you are asking that for peptide, so we have separate panel for that one that is called peptide QSA. So I can go, right? If I type in the task button, there is a peptide QSA. So it is basically same thing. And just open this panel. You can load the sequence and the observable. So either you can load it from here, or if you have some Excel file or CSV file with the sequence and what will the peptide response or whatever that is your observables, and basically same panel, right? So you define training set, test set, and just run the build the model, and it will have the same kind of analysis. Okay, so for peptide, uh, the important thing is that how we'll generate the descriptors, right? So for small molecules, it will have all the descriptors. And for peptide, I think we already have 250 descriptors there in Schrodinger, 280 or something. Some are like sequence based, some are structure based. So if you provide the structure of the peptides, it will also generate the structure based descriptors. If you only put the sequence, it will only give you the sequence based descriptors. And then it will build your machine learning or QSR model. Okay. Yeah, but the analysis part is basically same. So that we're going to see. Yeah, it is still running. Yeah. Any other questions? Can you please tell about the quick prop it used and it's to be which stage in the beginning or at the last? So quick prop. Okay. So since you guys are asking quick prop, so I'll go to the panel quick prop. Yeah. Right. It will, if you select any of the set of ligands, it will generate some I think 700 or something different properties of this ligand. Okay. And the idea of QuickProp is that there's a, you guys know Lipinski's filter, like there's a basic 5 filters for drug-like properties. L of P, hydrogen bond donor acceptors, right? So if you're working with a very large data set, right, 1 lakh, 2 lakh compounds, and for some properties, you need to filter out all those compounds. You can generate the QuickProp, all the properties, and based on some property that is you don't want to see, or some cutoff value, you can define that cutoff value and then take for the next stages. Okay. And also some cases it will give you the toxicity admit some kind of quantity or the property. So basically, yeah, if you are working with the very begin like very large data set or very beginning, designing your compounds or generating library, after generating the library, you can filter out by some property using this QuickProp. Can you suggest any databases or libraries of peptide inhibitors? Uh, yeah, I'm not sure about the peptide inhibitors. Yeah, I don't know, Sophie. Yeah, but we can Google it. Yeah, there are some. I think from literature you can get some data set. I worked very long time ago, but yeah, I right now I don't remember anything. Yeah, so my job is completed. So I'll go to the QSR panel. My job is completed. So I'll just explain that one and you can also see. So after building the model, I want to go to the view model and make prediction. Right? The first stage was that I build the model. Now my job is completed. Now I can view the model. Okay. So one thing important is that while viewing the model, I just click all this 36 compounds again. Okay. So all these are 36 I have selected. So the only option is that from file, right? So I can browse it, and in that working folder, it will create this build task, the name that we have given. Inside that folder, there will be a .qzip file. Okay, you need to open that file. I'll again repeat. If your job is completed, you need to browse it, go to the view model, browse it. Inside that your working directory, there will be a folder called build task underscore one. Go there and there will be QZip file where all the models are saved, top 10 models, and open that QZip file. All right. And you can see already some statistics are here. 4 Q square. You can also, there's a plus symbol here. You can expand that one. So I just click the plus here and you will get all these different model score Q square value. So I'll explain that one. So also there is an option called show more. So I just click that one. More statistics you will get. Show less and show more. So what is telling me that the model, this is the first model. It is using the kernel-based partial least square method. That is the algorithm it is using, and it takes the radial fingerprint. That is a descriptor. Okay. So if you go back and check what is radial descriptor for molecules. Okay. And it is a model number 9. So out of 50 model, it is a model number 9, which gives the best score, overall score, standard deviation with respect to the experimental activity, R square. R square is for your training set. Right? If you plot, this is a least square method, partial least square. This is nothing but your fitting the lines. Y is equal to mx plus c. Right? So the R square is your this M value. And then RMSE, root mean square, in root mean square error, that is with respect to the your experimental value, and the Q square. So Q square for your test set, the R square value, but for the test set. Okay. Always give importance to the Q square value. If I just put less here, it will only highlight the Q square. Q square is nothing but R square, but for test set. Test set, you remember, after building the model on the training set, it will have the test set, and then it will predict for all your test compound. So that will give you the accuracy of your our model. So always give importance to the Q square value. The last one is that Q square, but for only for molecular weight as a descriptor. That is called the null hypothesis. So in this particular case, it is only taking the molecular weight as a descriptor and then build the model. Okay. So all those Q square R square closer to 1 means that if the model is performing good, right? It's fitting the your straight line. And you can see the molecular weight is 0.04, which means that there is no correlation between your predicted activity and the experimental activity. All right. In this case, this is a base model, 85% accuracy to the test set, and this will give the overall score. Okay, combining everything, finally it will give some score, and the final score is talking about your overall score. Same thing for the second one, right? So that is how I'm going to explain the result. There's an option called report details. So I just select my top model here. I'll go and report details, and it will give you the more detail of your that particular model. So this is my model, first model, KPLS radial 9. For the training set, what is R square? For test set, what is a RMSE and Q square, right? And this will tell that compound 1, ligand 1, this is in the training set. Observed value or the experimental value 5.50, right? That is a value 5.509. Yeah, 5.509, and predicted is the 5.42. What is the error? The difference between that one and the compound name. So it will give me more details of this, all the compounds. I can also do the scatter plot here, right? So it will plot here both the training set and the test set, and the red line is y is equal to x. Okay, 100% correlation means that y is equal to x, this diagonal line, and these are my blue color in my training set, red are my test set. Okay. The other option is that visualize model. This is very important. Someone asked that how you can uh, design molecule or repurpose the drug. So this will be very useful. If I go to the visualize model, remember you need to select all those compounds. Then it will have this picture. Select everything, all the compounds here. Then go and visualize model, and it will give you this kind of color code. So for this now, I'll just go to none. Right? Earlier we did the reference, but this case none, and you can see different color region here, blue and red. This part is blue, some part, right? Also the experimental activity, and this is predicted activity. Okay, so the blue and red color or the circles, that means that if you have the red color here, that are positively contributing towards your biological activity. If you have blue color, some part, if it is blue color, highlighted by blue color, those are negatively contributing towards the biological activity. Okay, you can see here this particular aromatic ring here, they are positively contributing towards your biological activity. So probably if you're going to change this molecule or repurpose this compound, probably should not touch this anywhere here. It will have a detrimental effect to the response. If there is a blue color region, those are negatively contributing, which means that you can change those part of your molecule to design the new compound. Okay, so that is how you're going to explain this result. And the next is that make prediction. Okay. So what we'll do, I'll just close this auto QSR panel for the time being. Okay. I'll just take this one, the first compound I have included, and I'm going to make changes in this compound by using enumeration. Like last year, I think yesterday you have seen this enumeration. I'll do that one very quickly. So I'll just randomly select this part of your my ligand, hydrogen. I'll go to, if you are not able to do this, I'll again repeat, don't worry. Then I'll go to the add fragments. I'll just click create illuminated entries. So I'll make changes to the default diverse arc group because it will take less time, and I'll run. So what I'm generating is that I'm generating adding some functional group in this particular position, and I'll have some compounds already in my workspace. I'll again repeat this part. Please close the AutoQSR panel, otherwise it will be very slow. I close the AutoQSR panel, then I included the first ligand here. I just randomly select for this case workshop. I just select this particular hydrogen here, where I'm going to replace some of the functional group. I go to the build, create enumerated entries, and for the time being, make changes to the diverse subgroup and run. And very quickly, you see that I have this 43 compounds, right? This is my first compound enumerated. CH group address here. This is the next group, right? So for these compounds, all these 43 new compounds, I don't have the activity. Okay, it just copied from my original reference one. Don't see this value here. This just copied from my original 5.5, right? So for this compound, I don't know the biological activity or the pIC50. I want to predict for those compound what could be the activity using that model that we have built. Okay. So I just select all the compounds here. Now I'll open the AutoQSR panel again. I'll go to the AutoQSR panel, right? And I'll plus here. So for the prediction here, right? Use structure from. So I have selected this structure, new structure, which I have just enumerated. So there are different model to test. I can keep the base model, which is this one, the first one, or I can keep all model consensus. So it will take all the models and build a consensus score. Okay. Or I can select any of those 2, 3 models and then build a consensus prediction. Okay, anyone will work. So I'll go with the maybe the first thing and I'll go to the base model and job setting. Very quickly it will predict. I will compute and run. So all these 43 compounds, it will going to predict the pIC50 value using that particular model that you have selected. Yeah, you guys able to follow, or I'll going to repeat this one. Just let me check. Yeah, I think mine is done. Yeah, so I have predicted for the new compounds. So what I need to go is that I need to go to the project table. So if I go to the project table, I'll just expand it. These are the new compounds. right? So for this compound, I'm going to see that the what is the result that I'm getting. Just select all. Yeah, I'll just drag it on the right hand side. It will be on the right hand with the name prediction. Where is that color? I'll deactivate everything. Just let me check where is that value. Yeah, so it will create a new entry unclassified. So predict Y. So I'll open that one, click that one. Where is Yeah, so you can see all those new prediction here. So for this compound, the first one, which is the new one, although it is predicting the what could be the PI50 value, right? It is here in the unclassified predict Y. Okay, so that is how we are going to predict for a new compound, right? You can design any compound, either enumeration or any other mean. If you have a good knowledge of chemistry, build any molecule, and from the auto QSR panel, right? If you see your model is good, take that compound and predict for that compound for the biological activity. Okay. Yeah, any question or any doubt? You guys able to follow? Yes, no. Yeah, those who are not able to follow, again, this recording, it will be shared with you. Maybe later point of time, you can go through this video, and maybe that time you have a clear idea of what is happening. Okay, it's very simple panel. In Schrodinger, all the panels are very simple. Like, so in the auto QSR panel, nothing you need to do. You need to first clearly prepare the data set. That is the important part in the QSR model, right? Take the some compounds, which compounds from literature or patent for your target that you are working. Take those compounds with the corresponding activity. It should be same unit. If you are taking nanomolar, or it should be nanomolar. If you are taking picomolar, or the unit should be same. Convert to the negative log unit. Give that input in a here, and then you can build a model. Okay. So this, I think, if you have any, with this, I will end the auto QSF talk. But if you have any question, let me know. And then we'll go to the next topic, that is the ligand designer. So see, are you here?
Yep.
Okay. Yeah, Kosik, then I'll log out. Or
Yes, sure.
yeah, so I'll log out, and then Kosik will take you to the ligand designer part.
Yeah, this is the last topic for today. We'll take another 15 minutes for this. Then we will wind up with session today. Okay. So thank you all for staying for all so far. And this last tool is quite important because so far we have seen docking, which tells you which are the active molecules, and MD can tell you which is the most active molecule. And you can build machine learning models for other properties also. But eventually, at the end of the day, you will have to modify the molecule to optimize some property, other property. So you're going to look at this tool called Ligand Designer that can help you design ligand molecules based on the protein binding pocket. Yeah. So just give me a minute. Let me launch my cloud instance. Any questions on what was covered so far? All right. I hope all of you can see my screen right now with the software. Let me close the extra stuff. This one, this. Oh no, I should not close that. Okay, let's see that. I hope. No, yeah, I closed it accidentally. Anyway, so we'll look at this tool called Ligand Designer. And for this, let me open the project that they have been working on before. So day two is there. Then I'll go to file, open recent. So do one thing. All of you try to load a different protein. So go to file, get PDB, and then the PDB ID is actually to save time. Let us not do that. Let me see file, import structures, and home, desktop, data, um, docking, MD workshop files, docking to P33. Yeah, fully prepared protein here. We'll take this protein, so I'll share the path in the chat box. What are you working on? That's okay. For now, stop all of that stuff, and then you can keep the same project. You don't have to change your project, but in the same project itself, you have to load a new structure. So you have to go to File, Import Structures, and once you're in that particular place, then you go to Home directory, Desktop, Data, Docking, MDE, Workshop, Files. Then in that, you go to docking underscore 2p33 folder. Once you're in that folder, load the protein file which says fully underscore prepared underscore 2p33.lne. Just load that file that is a prepared protein complex. So for this tool, for ligand design, we have to have always a prepared protein complex. Let me know if you have any difficulties finding that particular file. I'll give you a few seconds to find that file. By now, you should know how to navigate through the cloud instances and stuff. So home directory, desktop, data, docking MD workshop files, docking to P33, and then just load the protein fully prepared to P33.MAE. So this particular molecule, this particular complex has a ligand bond to it, and you have a protein also. So for this tool for ligand design, you have to have a prepared protein complex. So once you have this thing loaded on the screen, go to task on the top right, then you go to browse, and you go to the section for lead optimization. And in lead optimization, you have a tool called Ligand Designer. So it's going to look something like this. There's a panel that pops on the right side. So I'll type the things in the chat. Tasks, browse, lead optimization. Then we go for Ligand Designer. Once you open these things, just click on the Analyze Workspace option, and that will give you a view that looks like this. I'm going to spend the next 10 minutes explaining to you what this particular, what you are looking at in the workspace right now. I hope all of you have loaded this particular protein complex and are able to analyze the workspace option in the ligand designer. If you haven't done it, please let me know. I'll wait for 1 or 2 minutes, then we'll go for the demo session. Has anyone done this? Okay. Yeah. So what you're getting here is that I have a ligand. I also have a few colors around the ligand. So if you look at the color coding, if you have a light blue color in the binding pocket, and this is the binding pocket of the protein, the light blue color indicates a cavity in the binding pockets. Cavity is empty space in the protein binding pocket where the ligand is not occupying as of now. And the dark blue color is a solvent exposed part. So you can see the color code in the top right. You have the light blue for the cavity and the dark blue for the solvent exposed part. What you're looking at right now is a growth space for the molecule. So these clouds that you look at is places where you can grow the molecule depending on what your interests are. So at the same time, if I turn off the growth space and turn on ligand receptor interactions in the panel, it will show you the amino acids of the protein that are nearby this particular molecule. So you can see that I get this particular view. And when I put my cursor on any of these amino acids, just look at my screen for the next few minutes. So don't try to do it at the same time. So put my cursor on any of these amino acids, you can see that it displays the exact positioning of the amino acid in the binding pocket. So if I put my cursor here, that is the position of those atoms. If I put my cursor here, there's a position of those atoms in the binding pocket. Similarly for this one, this one, this one, and this one. So it also tells you at the same time what kind of atoms do you have in the vicinity of the ligand. So here I have hydrogen bond acceptor, here I have hydrogen bond donor, I have one more acceptor here, hydrophobic groups here. So you can see that you have all these different groups. If you have aromatic rings, it will show that also. So all of these are available for you in this particular interface. And on top of that, if I put my cursor in any of these things, you can find out if it's interacting with the backbone of that amino acid or if it's interacting with the side chain of the amino acid. If you know your chemistry of all these 20 amino acids properly, you can clearly find out if it's in the backbone of the side chain. For example, if I put my methionine, this thing here, it's interacting with the NH group of methionine. So methionine side chain has a sulfur. NH group is only present in the backbone. So that's why I know that it's interacting with the backbone of methionine here. Similarly, if I put my cursor on this residue here, you can see that there's a glutamic acid and you have C double bond O minus. That means it's interacting with the side chain. The side chain is facing the molecule here. In addition to this, if I turn on the ligand surface and turn off the ligand interaction, you can see that the ligand, it shows you different colors. You have a dark blue color, you have a dark red color, you have a green color, you have a yellow color. So dark blue indicates a hydrogen bond donor region in the protein, in the ligand, sorry. And the red indicates a hydrogen bond acceptor region in the ligand. So this nitrogen is an acceptor, this amine is a donor. Similarly, if you have a green region that is hydrophobic, if you have a yellow region that can be aromatic region on your molecule. If I turn off the ligand surface and turn on the receptor surface, you will see how the receptor surface looks like for this particular protein. And yesterday I mentioned to you that you have to optimize for both the shape and interaction complementarity. So if you want to look at the shape of the binding pocket, you can see that if you rotate this receptor surface, there is a very narrow groove into which the ligand has to go and occupy, right? And this narrow groove, where the gap is only this much, is also deep. You can see how deep it goes into the protein binding pocket. So if you want to complement the shape of the binding pocket appropriately, you want to make sure that you have the ligand atoms going into every groove in your binding pocket. So here you can see that the surface of the receptor goes all the way till this end, but only have ligand atoms still here. So if I turn on the growth space, you will notice that the light blue cloud, where we have a cavity, the cavity is present exactly in this region where the ligand only goes till here, but the receptor surface is all the way till the end of this. If you can make some changes to the molecule and try to grow in this direction, so you can fill the cavity, you may have a better chance of it interacting with some residue on this side here. So I can turn the ligand receptor interaction also. You have a few amino acids here. So if you grow your molecule in this direction somewhere, you can try to maybe form some interactions with some amino acid in this vicinity here. Right. So the receptor surface like this is very useful in trying to look at whether you have a molecule that can fit in the binding pocket appropriately or not. Once it fits in the binding pocket and then you form good interactions, then you have a good molecule to interact with the protein per se. If you turn off the receptor surface and turn on the pathfinder options, it tells you which bonds in the molecule can be broken to result in individual reactants. The other way to look at this is that if you want to make this whole molecule, you have to first form a reaction between this group here and this group here. And then you have to form a reaction between this group here and this group here. And then you have to form a reaction between this entire thing here and this thing here. So it also tells you what possible reactions you have to follow through to synthesize this molecule. The pink colored bonds indicate which can be broken in this molecule. If you turn off the pathfinder bonds, if you turn on the ring systems, it tells you what all rings you have in the system. You have these 3 aromatic rings, and you also have one more ring that is not aromatic. And these rings can be modified later. I'll show you what changes to make later. So by default, most of the time people look at the growth space and they look at the ligand receptor interactions to figure out what new interactions can be formed between the ligand and the protein. And so let me just check this. Ligand receptor, that's all fine, right? So we got this information right now. And what we can do is, if you just also look at just below this section here, there is also a section called multi-parameter optimization. In this section, you have a pentagon with 5 different properties. So you have log-P, you have molecular weight, you have hydrogen bond acceptor, hydrogen bond donor, and polar surface area. You can see there's also inner pentagon in this, in the green color pentagon. This green color pentagon should not cross the boundaries of the bigger pentagon. If it does, that means it exceeds these values that are typically recommended for these properties. And just below this pentagon, you see that it reports the exact value for that molecule. So log P for this molecule is 3.9, number of donors is 3, molecular weight is 398, surface area is 85.9, number of acceptors is 4. And next to each of these numbers, you also get in brackets, there is a small range that is given, and that is the optimal range for these properties. So if any of these properties is going out of bounds, it will be displaying this property number in red color. And finally, you get something called this MPO number, which tells you on a scale of 0 to 1, how likely your molecule is to be a good drug molecule. So 1 is a good molecule, 0 is not a good molecule. In addition to these 5 properties, if you want to add other properties, you can click on this wheel option here. And we have this 5 selected by default. If I scroll down on the right side, you can see there are other properties also like number of chiral centers, rotatable bonds. Oops. Number of chiral centers, rotatable bonds. You can see now that the pentagon moved to a heptagon because I added 2 other properties. You can also add like one more, so it becomes an octagon. And then if you go to 9 different properties, the polygon is not showed anymore, but it shows you the properties on in this case here, and you can still see the MPO for all these properties that are optimized, right? So up to 8, you can see the polygon, but after beyond 8, it doesn't show the polygon, but it still calculates properties for you. I will turn off these other ones. I'll go back to a pentagon, and you can also try to. So this MPO is determined based on this custom scoring function. You can try to change the custom scoring function to some other number like sequence key or drug-like, lead-like, whatever you want to use. You can do those things. And you can change the threshold values also for each of these as to what you think is a good number and what is not a good number. Right? So you have this full control for these things. So I won't change any of these properties. I'll just keep it as it is. So once I have this information, so far we have been making changes to the molecule randomly. We don't know if the change is going to be beneficial or not. So in this case, what we will do is, I know that for this particular molecule, if I hold on, there are a couple of interactions between the ligand and the protein. Let me just try to find out where they are. It should typically shows it here in the workspace itself, but for some reason I can't locate it. Let me look at the interaction diagram. So It forms interaction with methionine 149. So where is methionine 149 in this case? It's 146. There it is, methionine 149. So if you put my cursor on this residue, you can see there's dotted lines that appear. That means this part of the binding pocket is very well covered. You can't form new interactions with the protein. And if you also observe, you don't have many amino acids on the solvent exposed part. You only have the residues on the cavity side of the protein. So if I want to, it depends on again what probably you're trying to optimize. If you want to optimize for potency, you want to for more interactions. If you want to optimize for solubility, you may want to change the area for the solvent exposed part. So depending on which property you want to optimize, you have to figure out where you want to change the molecule and what changes you have to make. That is something that has to come from your intuition. The software can't do it for you. It's only guiding you as to where you can make the changes and what changes. It only provides the tools for making the changes. So where to make changes, what changes to make is something that you have to have an intuition for, depending on what you're trying to optimize it for. Once you have done that, then you have this workflows option where you can go to the workflow and you have this different workflows for attaching bar groups, filling a growth space. I'll show a couple of them here. Then you have workflow for biosafety replacement, or you can, if you are have water molecules in the binding pocket, if you run a tool called WaterMap, which is an advanced MD tool, then you can try to replace or displace a water molecule that is not stable. You can form a ligand interaction. You can swap your ring molecules. So you have these 3 rings, 4 rings in the molecule. You can swap any of them with this ring swap beta option here. You can cyclize a molecule. You can edit a molecule manually, and all of these things can be done. So I'll show you simple workflow like attach R group, which you have explored so far. So if I click on this attach R group and I see that there is a cavity here, and I want to fill this cavity with some group, right? So when I click on the attach R group, it says select attachment bond. Right? So I have to select which bond I want to change in this thing. And since I want to grow this particular cavity, I'm going to click on this atom, this hydrogen atom on the screen. Just hold on, this one here. Once I do that, you see that there's a yellow colored arrow that appears. And this means that I'm going to make derivatives of the molecule in this region only. And I'm doing it in the presence of the protein. So once I click on this atom, it's going to see that it shows me the option to enumerate. Before clicking on enumeration, go to settings. And once you go to settings, it's going to load the libraries for us that we have seen before for the R group enumeration. Then you go to custom. And in custom, since I have this, my intuition, maybe your intuition will be different. I have a few hydrophilic groups here. I also have an acceptor here. And I have one more acceptor here. Maybe if I grow this and make it a hydrogen bond donor group, then maybe I can form interaction with either of these acceptors. That is one hypothesis. I don't know if it's going to work or not, but I can try it out. So to do that, I'm going to, from this custom library options, I'm going to choose the groups that can form a hydrogen bond. There are 143 groups in this particular section. I'm going to try to evaluate them one by one. So I'll choose this option here, click on save, then I click on enumerate. Once I do this, you can see on the bottom right, it says enumerating new ideas. You have 143 ideas in total, out of which it has so far done like 3 or 4. And for any new idea that you get that works, you're going to see the molecule modification here on the left. So now it is generating this design of molecules on the fly, depending on the options that I have chosen. I have chosen to change this area here, and it is making the changes. So far, out of 65 or 68, around 32 of them worked. The remaining ones haven't worked. Let us wait for it to finish. Then I'll show you how to look at the results for this calculation. So we're making like guided changes of the molecule based on what residues in the binding pocket. 138, 140, so it's done. You can see that it produced 35 poses. 106 ligands failed to dock. They will fail to dock because there is not enough space for the molecules to fit over there. Right? So for the ones that succeeded, they could fit the molecule in the binding pocket. So if I click on this circle here, you will see that what changes were made to the molecule. And now you can also observe that there is a small bad clash here, which means this atom is getting close to this protein atoms over there, or some other atom in the back end. I can also click on some other molecule here, click on the circle in front of it. You can see all the changes happening one by one. And some of these changes can result in new interactions. So you have to evaluate like which ones can be better, which ones are not better based on interactions.
At the same time, you can also look for the shape complementarity like we had done before. You can see that now the blue colored cloud is decreasing as I increase the size of these moieties in the group. While the changes are being made, for each of these newly generated molecules, you can also see what the properties are. So if you click on the circle, notice that these values change for each molecule. When I load a different molecule, you'll see that it has different properties. So it calculates them at the same time. You don't really have to use some other tool if you're interested in these basic properties. Use Ligand Designer, make a change, and that's going to predict these properties for you for every change that you have made. So there's one workflow where you can use the attach R group option to change it. So for some reason, if you have a ligand surface being shown, then just like show it and hide it again. The other workflows would be that, let me just slowly minimize this. And the other workflows would be that I can go in the field like growth space. The advantage of this option is that I don't have to pick which one to choose exactly. So if I put my cursor on this right now, it identifies a cloud. You can see these yellow colored clouds around this ligand. So these are all growth spaces where you can grow your molecule. And once I have these things, so I can, let's say I want to like make the molecule more soluble. So maybe if you want to make it more soluble, I can change this carbon ethylene group here to some other thing. So maybe I can try to like click on this area of the group. And once I do that, you get a pop-up saying explore ligand side chain to fill growth space. Just click on OK. Once you do this, it shows you all possible changes you can make near the growth space. So you can either like change this atom here, you can change this atom here, you can change this atom here, you can change this atom here. You can try to break this bond and try to have a new fragment altogether. All of these are possible changes that you can make to the molecule. So it highlights like what all changes you can make, but you have to choose which of out of these changes, which one to pick. So that again comes with intuition. I'm going to choose this one. And if I choose this one, again, you get the same enumeration panel. You go to settings, choose the kind of enumeration you want to do. So I want to make it more soluble. I can add like solution R groups, click on save and click enumerate. Now it's going to enumerate like 33 groups here. And if anything succeeds, I'm going to have the output on the left side again. I think in this case, nothing worked. So all of them actually have failed. So not every change, your intuition could be wrong. That is something that you gain by experience. So in this case, for me, it didn't really work. Maybe I should like break this bond here and then try to change it. So I think I changed this particular atom here or with this atom here, and there's not enough room to occupy this pocket here because it's clashing with this atom. So you have to have that picture. And once you make a change, you'll notice that if it's correct or not, depending on what results you get. Similarly, if you want to swap the ring systems, you can try to click on the ring systems option here and go to workflows and choose ring swap beta. Then it's going to give you an option to change the rings. Hold on. So I click on the ring of my interest. So I can select this one, this one, this one, or this one. Let's say I want to change this ring. You click on this, and now I have the option to change the ring to something else. Click on the settings here, and you can change it to either aromatic monocyclic rings, aliphatic monocyclic rings, aromatic bicyclic rings, 5,5 or 5,6 or 6,6 rings. So it's up to you. You can click on this. Let's say I want to change it to aromatic monocyclic rings. I click on OK and I click on enumerate, and I'm going to get the output where this particular ring is going to be changed to some other format. You can see it says running ring swap. Once the job is done, you're going to get the output. Keep in mind that there's a beta version, so we're still testing this particular workflow. So be aware, like if you're a good medicinal chemist, you'll know like once you have done this thing, whether it's going to be correct or not. So it's still running it. Once maybe it will take some time. So you can do all of these things, but there are so many ring systems. So I can click on this one of these outputs here. Let me just stop it. There are 830 ring systems. That's too many. I'll just stop this. And I'm going to click on this first output. And that's a different ring that I have just changed over there, right? So you can do such kind of calculations very simply with the software. Every time you make a change, you have to see if it improves the interaction pattern or not. And once you think that you have a better molecule, you go back, do the docking of the molecule, like we have done yesterday, and then you go for MD simulation if the molecule seems to be promising after docking. So with this, the workshop is over. So you can practice this ligand designer. I hope the interface is quite simple. Most of these buttons, right? If you're not sure exactly how to use the buttons, for every panel in Schrodinger, you'll have a question mark on the bottom right. So in this case, it's just like hidden below it. Let me just pop this panel out. You can see the question mark here. If you click on the question mark for this panel or even protein preparation, it will take you to a manual, have the question mark here. It will take you to a manual that provides detailed explanation for each of these options in the panel. To give you an example, let me just show you how a manual, the manual looks like for a particular panel. So let's say, take this and if I show you this, this is the manual, one of the manuals here. And in the manual, if I look at this, I can just search on the top. So let's say I want to explore protein preparation. You can just search for that. And it's going to take you, like you have the panel option here. If you go to workflow panel, then you have the features for each of these things. If you click on this, it tells you what all features in the preparation workflow tab. And once you go there, click on features again, you see that for every option in that particular panel, you have detailed explanation as to what each option does, right? So if you're not sure whether to choose a given option or not, always read the manual, and that will help you clarify that particular concept. And for you to access the manual, you need to probably have an account on the website. So we have covered quite a few things in the workshop in 2 days, right? But we also haven't covered many other things in the software. If you go to task, we have so many tools here. And for each of these to cover, as I told you, it will take a long time. But for your project, you may have to use some of these tools. The best resource for this is that if you go to our website, you can just go to schrodinger.com. And in this case, once you go to the website, you can go to life sciences and go to resources, and you have the option for going to tutorials. So if you go to tutorials, we have quite a few tutorials available. For example, if you want to do docking calculations with Glide, you can click on the first tutorial that is listed here, and it will take you to a page where you can download example files for the tutorial. And if you scroll down further, it's going to show you, like, give you some background as to why you want to do these things. And also it's going to give you like screenshots of the software along with step-by-step instructions as to what exactly you have to do for each stage of your workflow. If you go back here again, you can try to search these tutorials based on the topic of your interest. There are so many areas we cover in the software. I only touched upon very, very few aspects of it. You can also try to shortlist based on the product. Like, for example, if I want to get all tutorials for Glide, right? I can just click on the Glide option here. It will show me all the tutorials relevant for Glide-based things, right? So all of these can be done with the tutorial section. And for those who are interested in material science, you can click on the material science option. You have material science tutorials also. In addition to these things, if you go to the resources section again, you can go to webinars. These webinars also like free of access once you have an account on the website. Activating the account takes 2 or 3 days. Try to log in with your institute email ID. So once it is activated, you can access all this information, tutorials, webinars, white papers, publications, all of this stuff, right? Including case studies also. So this is the best repository for you. First, try to work on some project. If you're stuck with using some particular option, click on the question mark to take you to the manual. If you're working on a new area that has not been covered in the workshop, I would recommend you to first check for tutorials for that particular section. And in addition to that, if you go to the documentation for these things, you also have like documentation for each and every module in the software that you can look into. So let me just try to minimize this. And even though we have used like quite a few of these through the different panels, for those who are interested, we also have lots of scripts available that you can try to use for your calculations. The GUI, the graphical user interface of the panels has quite a few default options that are there. But let's say you want to use more options, you want to have more functionality, then you can try to access them from the scripts as well if you're interested. But this is mostly for advanced users. I don't recommend it for beginners. You can also filter based on applications, depending on what you want to do. All of this stuff can be done very easily with the software. You can click on small molecule drug discovery. Once you open that, then you go for the task that you can perform, and every task that you can perform, you can see that you have panels for lick prep, protein prep. If you click on these things, you can either look at individual sections here. So it's very, very detailed. So just try to go through these things and finally try to explore it yourself. If you're stuck for more than 1 or 2 days, please drop an email to us and we'll help you with your queries. Sometimes we'll help you by email. Sometimes you can have a Zoom call for your particular project, depending on what kind of issue you're facing. I'll send the instructions later for who to email and things like that by email. And I'm going to also send you the recordings probably in like half an hour or so for all of these topics that we covered. Any questions about the workshop? We won't have time to cover QIK prop, but that can be addressed in the tutorial section. So go to tutorials, you'll have a tutorial for QIK prop calculation. Keep in mind that we're not just here for 2 days. We are there to support you as long as you have the license available. So anytime you have any query, drop an email to us. If you are a student, you have to CC your guide in the email to us. If there are no more questions, I think we can conclude the workshop. I'll wait for a couple of minutes. The cloud instance will be open for practice for tonight also. So, but tomorrow morning, I think it will be closed. So try to see if you can do that. Can we export the design images? Yes, you can do that. So if I go to this option here, you have the workspace option. And if you go to workspace on the top, you have the option to save image. And in the save image, you can try to go to options and you can choose the DPI that you want to use and the size of the image and click on give a file name and click on save. I'll repeat again, go to workspace, save image as, then you can go to options here, choose a DPI, choose the size of the image and click on save. Any other questions? All of you who are in this workshop today have access to the software at your institute. Please reach out to the concerned person to access it at your place. Thank you, ma'am. If there are no more questions, I'll wait for 1 more minute. We'll complete the workshop after that. Thank you all for joining in. I know it's a lot of things we covered in 2 days, but I hope this is the beginning for the journey for all of you. Thank you all. I'm in the meeting now. Thanks all for all the kind words. Bye.